Hello friends, today we are going to discuss few questions of year 2019, and this is the, you can say, part 3. We have already completed part 2 of 2019. This is the third part, and here we are going to discuss total of 5 questions, and these questions are from the mains. So the first one, it is asked that a light wave is incident normally on a glass slab of refractive index 1.5. If 4% of light gets reflected and the amplitude of electric field of the incident light is 30 volt per meter, then the amplitude of the electric field for the wave propagating in the glass medium will be. So here it is talking about the, you can see, intensity of the light in terms of the electric field. Okay. So we are going to use that formula directly and start from there only. So we know that intensity of a light ray in the air intensity of light ray in air, and if represented as I, then this I will be equal to half epsilon naught E naught square and multiply by C, where E naught is the permittivity of the air. E naught is the permittivity of air, and epsilon naught is the permittivity of the air, and E naught is the amplitude of electric field in air. Amplitude of electric field in the air. Similarly, we can write the intensity of light ray in a glass medium, or we can say in any medium. We can say intensity of light ray in a glass medium, and if that is represented as I prime, then this I prime will be equal to half epsilon, and this is our E square multiplied by V. Here epsilon is the permittivity of the medium and V is the speed of the wave in the medium. Here epsilon is the permittivity in the of the medium, and V is the speed of the wave in the medium. Speed of wave in medium. And we also know the relationship between epsilon, epsilon naught, and epsilon r. So we can just write that relationship also. And we know that our epsilon is equal to epsilon naught multiplied by epsilon r, where epsilon r is the relative permittivity and rest two parameters we have already explained. So this ER is the relative permittivity of the medium. Therefore, we can write the equation that our I prime will be equal to half epsilon naught epsilon r and E square multiplied by V. And we are given that 4% of the light is reflected, so it means rest of the light is absorbed or is passed through the slab. So we are given that 4% of light is reflected, therefore we can write that intensity of light absorbed will be equal to remaining, that is 96 divided by 100 and multiplied by I. That was our total intensity. And and we substitute the value of the I and I prime, we can get that our half epsilon naught epsilon r E square V will be equal to 96 upon 100 multiplied by half epsilon naught E naught square and multiplied by C. And we can now simply solve it. We can write our E naught and E naught, half and half goes away. So from here we can write that our E square, which we are required to find out, will be equal to 96 upon 100 multiplied by E naught square divided by ER and C divided by V. And or we can say this E will be equal to square root of this. And if we substitute the value, we also know that this C upon V is equal to mu. Okay. And our ER, here it is square root, will be also equal to mu. And if we substitute these values, we get that our E will be equal to 96 upon 100. E naught is given to us 30, and this comes as mu upon mu and its square root. And from here this E comes approximately equal to 24 volt per meter. Therefore option number D is the correct option. Option D is correct. Next question. The eye can be regarded as a single refracting surface. The radius of curvature of this surface is equal to that of a cornea, that is 7.8 millimeter. This surface separates two media of refractive index 1 and 1.34. Calculate the distance from the refracting surfaces at which a parallel beam of light will come to the focus. So here basically we have three different refractive indexes. Okay, so we can just use the you can say the formula, and and it is separated by two different medias. So we have two different medias, refractive index 1 and 1.3, and the radius of curvature is given to us as 7.8 millimeter. You can say our radius of curvature, that is of R, is equal to 7.8 millimeter, and refractive index 1 is of air, so therefore we can write that our mu1 will be equal to 1, and another one we can assume that is a mu2, that is equal to 1.34. And here it says that the ray of beam which are coming are parallel, therefore apni where we can say u will be equal to infinity. So here u will equal to infinity. So we can use the formula, and which gives us that mu2 v minus mu1 u is equal to mu2 minus mu1 upon r. Here mu1 is our refractive index which belongs to the incident medium, and mu2 is the refractive index which belongs to the refracting medium. We substitute the value. Mu2 is our 1.34 v minus 1 upon infinity. It comes as 1.34 minus 1, and r is our 7.8. And we get this as that the v will be equal to 1.34 multiplied by 7.8 and divided by 0.34. This gives us that the position of the image v will be equal to 30.74 millimeters, and the answer is given in centimeters. So we can write that the v will be equal to 3 point close to centimeters. So option number C is the correct one. Option C is correct. We come to next question. It says that consider a tank made of glass, refractive index 1.5, with a thick bottom. It is filled with a liquid of a refractive index mu. A student finds that irrespective of what incident angle I is for a beam of light entering the liquid, the light reflected from the liquid glass interface is never completely polarized. For this to happen, the minimum value of mu should be. Okay, so we are given this figure. Here angle of incident is given as I, and we have, you can say this is our liquid glass interface, and the glass is having a refractive index of 1.5, and liquid is given as refractive index of having a mu. And here it is talking about the polarization, and for the polarization we are going to discuss, you can say, the relation between the Brewster angle and the critical angle. Okay. So we have to find the minimum value of mu, and this minimum value of mu will be decided by the relationship between the Brewster angle and the critical angle, and that relationship is that the, you can say, sine of critical angle is always less than the sine of the Brewster angle. So you can say that relation between Brewster angle and critical angle and this relationship is our sine of C is less than sine of IB. Okay. Here IB is our Brewster angle. Let me write this IB, and the critical angle is represented as C. So we are going to use this relationship, and we also know that for the critical angle that our sine of C is equal to 1 upon mu. And also we know the relationship that our tangent of the Brewster angle, that tangent of IB, will be equal to mu naught relative. Okay, that is a relative refractive index, and this relative you can say refractive index will be equal to the refractive index of the liquid, that is given to us as 1.5, glass, it is given as 1.5, and that for the liquid interface that is given as mu. Okay. So you can say mu of G divided by mu of the liquid. So this comes as 1.5 divided by mu. And so we can just modify the equation that is given to us, that sine of C is equal to sine of IB. Sine of C is our 1 by mu. So we can write our 1 by mu should be less than, and we know that our tangent of IB is equal to 1.5 divided by mu. So from here we can find out sine of IB, and that will be coming as 1.5 divided by our mu square plus 1.5 whole square and its square root. And this we can sort it out, and we can write this as mu square plus 1.5 whole square square root is less than 1.5 times mu, and if we square it both sides we get this as mu square plus 1.5 whole square, and this comes as 1.5 whole square, and if we have this as mu square, and mu square we can take as common. So this gives us mu square will be equal to, this will be our 1.5 whole square less than mu square, and this will be 1.5 whole square minus 1, and this we can write it as that mu will be less than equal to 3 by square root of 5. Okay, so the only thing we have to take care of is that the Brewster angle relationship with the critical angle. The rest of the things are quite simple to follow. So we get the minimum value of mu will be equal to 3 square root of 5. So option number A is the correct one. Option A is correct. And next question, it states that the variation of the refractive index of a crown glass thin prism with the relative to wavelength of incident is shown. Which of the following graphs is the correct one if dm is the angle of minimum deviation? So this is the graph given to us as per the question. Here as lambda increases, the refractive index decreases almost exponentially. So this is the given graph, and we have to find out the angle of the we can say graph for the angle of the minimum deviation. Okay. And we know that the the refractive index for a dm is the minimum deviation. So we can write that our mu is equal to, we have this as sine of a plus dm divided by 2 and sine of a by 2. And you can say for small angle prism, as in question, we can say that we can use the approximation for small angle approximation, and according to that we can write that our sine of theta is approximately equal to theta. So we can write that our mu is approximately equal to a plus dm by 2 divided by a by 2, and this we can write as 1 plus dm by a. And from here we can write that our dm, that is the minimum deviation, will be approximately equal to mu minus 1 and multiply by a. Okay. And we also know, as per the given graph or in general also, that the refractive index is dependent upon the wavelength. Okay. And for normal dispersion, as the wavelength increases, refractive index decreases. We know for normal dispersion, as wavelength increases, refractive index mu decreases. Or we can also write that our d mu by d lambda will be less than 0. Therefore, let us call this as equation number 1. So we can modify our equation 1. You can say from equation 1 we can write that our dm, which is a function of a lambda, can be written as refractive index is also a function of lambda minus 1 and multiply by a. And we can simply derivate it. We can write dm with respect to lambda will be equal to, and this will be equal to over a multiply by d mu lambda divided by d lambda. And we already know that d mu lambda by d lambda is less than 0. So from here we can say that our dm by d lambda will be also less than 0. So which basically means that as lambda increases, dm is bound to decrease. And based on this, we can say that the only option, that is the option number C, is the correct one. Option C is correct. Next question. It states that in Young's double slit experiment, the light of 500 nanometer is used to produce an interference pattern. When the distance between the slits is 0.05 millimeter, the angular width in degree of the fringe formed on the distant screen is close to. So we have to find out the angular width in this experiment, and we are given the wavelength as well as d. Okay. And we know that for if the angular width is given as theta, then this theta is approximately equal to lambda divided by small d. Okay. And we can just convert it to the required format. So we directly is based on formula, so we can write that angular width in radians, so we can write that theta will be equal to lambda by small d, and we substitute the values. We get theta is equal to lambda is about 500 nanometer and d is given as 0.05 and millimeter. So this gives us that theta will be approximately equal to 10 to the power minus 2 radians, and we can convert into degree. So we can write that theta will be equal to 10 to the minus 2 multiplied by 180 upon pi, and this will be giving us that theta is approximately equal to 0.57 degrees. So option number B is the correct one. Option B is correct. So these were the question which was asked in the year 2019. So all the questions for 2000 mains are completed in this third part. Rest of the things we already converted, you can say completed in first two parts. Thank you.